As we start chapter 5, we need to understand that it's really about our ability to communicate with each other about the compounds that we're discussing. So, our aim here in this very first section is to understand why it's necessary to have a system for naming compounds. So we talked about things like this before when we were looking at the SI system. Remember, the International System of Units was necessary because it allowed us to speak to each other about the units that we were experimenting with. And similarly, the same thing applies with Chapter 5 and what we call nomenclature. So why is a system necessary? Different types of compounds can be formed, and it's important for us as we're communicating this through names and formulas of compounds that we understand what those names and formulas are referring to. So for example, we have the first type of compound, which could be a metal and a non-metal. And then the second type of compound, these are the two main classes that can be two nonmetals put together. Now these are named in different ways, so that helps us differentiate between the two types of compounds. So before we get started, we need to label our periodic table in a way that will help us remember how to name different types of compounds. So the first thing we want to look at are the charges that we labeled in the last chapter when we were looking at how to turn atoms into ions. So everything in the first group, and remember group is vertical, up and down, everything in that first group has one electron in its valence shell, which means it's going to lose that electron to have a full inner shell, which is where it's stable. So remember, the numbers at the top that we're labeling here are not going to be electrons in the valence shell, rather they are going to be charges. So we're taking out that step of labeling the number of electrons in the valence shell and skipping right to labeling each group with its appropriate charge. So everything in the first group has a charge of +1. Everything in the second group has a +2. And if you need a refresher for how to label each of these groups with the appropriate charge, go back to that part 1 video from chapter 4 that we looked at. Remember, we skip this area in the middle that are known as the transition metals because their charges are a little bit more unpredictable. So we're just labeling the main group elements. So we skip over to the boron group, that becomes +3. The carbon group is ±4. And then we go back down in the other direction. Nitrogen is -3, oxygen -2, fluorine -1, and anything in the noble gas column is 0. It's not going to gain or lose because it already has a full outer shell. The next thing that we want to label is where the metals and nonmetals are divided on the table. So we see the metals are on the left and the nonmetals are on the right. The left and right of what? So you should see in a periodic table that you have, and if you don't, take a minute to draw this line in. There's a line that looks like a staircase that divides the left side of the table from the right side of the table, and it's not an even divide. But what we see is that everything on the left of this line behaves like a metal and has characteristics of a metal, and we will get into that a little bit later. Nonmetals, those things on the right of that stair-stepper line, also include hydrogen. So hydrogen is also part of that non-metal group. So metals on the left of that stair-stepper line, nonmetals on the right. We want to isolate tin, SN, and lead here. Remember in the in part 1 of the last video where we were talking about ions, we talked about this ±4 column and how it behaves just a little bit differently. So this is one of the reasons that this ±4 column behaves a little bit differently. Tin and lead have their own charges, and they can have multiple charges that aren't necessarily going to be only ±4. So we will talk about those later, but their charge is not completely dictated by the label of that column. So this is an exception that we need to discuss. The next things we want to look at are zinc and silver. And zinc and silver have set charges. So everything in this transition metal area in the middle usually has multiple charges because it can behave in multiple different ways. However, zinc and silver don't follow this rule. So just like tin and lead are the exceptions to the carbon group and the plus minus 4 rule, zinc and silver are the exceptions to the transition metal rule. So these have set charges. The charge on zinc is +2. The charge on silver is +1. Zinc and silver have set charges, just like everything in these first two columns over here have set charges. They're only going to have one type of charge. The first type of naming we're going to look at is what's called an ionic compound. And an ionic compound is formed from two different types of ions. And we're going to be looking at what happens when we take a cation, or something with a positive charge. Get it? Cation, positive. Take something with a positive charge and combine it with something with a negative charge. So our next section, 5.2, is to learn to name ionic compounds of a metal and a nonmetal. So we are taking something from the left side of the table, a metal, and combining it something from the right side of the table, a nonmetal. So type 1 ionic compounds, like we said, metal and a nonmetal. Cations are positive and are named first. This takes the element name. You do not have to change the element name at all when you're taking it from the periodic table and putting it in terms of its formula name. The anion is named second. It uses the root of the anion plus an IDE ending. And that root can vary depending on what the element is. You're not always going to be taking off the same number of letters at the end of an element, and that just takes some practice to be able to recognize. But for example, we see something like NaCl. This is made of Na, and it's also made of Cl. We can locate their names on the periodic table, and then we can see that Na is sodium and Cl is chlorine. But what we would need to do in order to observe naming rules is to take off the INE ending of chlorine, and we would change that to IDE. Next example would be something like Ki. Ki is made of K and I. K is potassium, so we would take that name directly from the periodic table. I would be iodine, as it's read from the table, but remember we're changing that ending from INE to IDE to signify that it's in a compound and not by itself. So Ki is then potassium iodide. And our last example is MgO. Mg, magnesium, and O, oxygen. But when we put this into its name form, we take the name magnesium and we don't write oxygen, we write oxide. So oxide instead of oxygen becomes the name of our compound. One thing I want you to get out of this is how the element symbols transfer to the formula. The reason we know we have two elements here is because our first element, remember, always has a capital and a lowercase letter if it's a two-letter element. And then we know that oxygen is our second element because that's where the second capital letter starts. So that's where we find our dividing line between our first element and our second element. So what we're going to do now is look at how to make a formula from a name. So when we have aluminum chloride, what we would want to do is write the symbols for both of those elements first. So we have aluminum, which is Al, and chloride, which is the same as chlorine, which is Cl. So what we have to remember, ionic compounds are neutral. So when we put a compound or when we put two elements together to form a compound, they have no net charge. Remember, that's what neutral means. It means no net charge. So when we write ions, we're going to have something that looks like this. Aluminum with a +3 charge, and remember we labeled this column in our table, and then chlorine with a -1 charge. But when we put these together, the whole point of this is we are canceling out the charge of the other one. So when we do this, we need to figure out how many aluminum equal the charge of 1 chlorine, or how many chlorine equal the charge of 1 aluminum. So we can see here, we've got a higher magnitude of charge with our aluminum. So we are going to need 3 chlorine to balance out the charge of 1 aluminum. 1 aluminum would give me the charge of positive 3. 3 chlorine would be equal but opposite to that. So that would mean I would need 3 chlorine, which would give me a charge of negative 3 with all of those chlorines combined to balance out the charge of 1 aluminum. I need them to be equal but opposite. So there's another way that we can do this, and that's what this formula is telling me. It's telling me that I have 1 aluminum for every 3 chlorine, similar to how something like H2O would tell me that I have 2 hydrogen to 1 oxygen. So that subscript becomes important here because the subscript is telling you how many of each atom you have. But if I'm looking at something like AlCl3, the 3 only applies to the number of chlorine that's in this formula. Doesn't apply to the number of aluminum. Notice there's no 1 on the outside of oxygen in H2O, and that's because the 1 is implied. It's implied because the letter is there. So if the letter or the element symbol is there to tell me that there's at least 1 there, I don't have to put a 1 as the subscript. So the other way to look at this is to take the charges and do what we call, or use what we call the crisscross method. So this takes the 1 on chlorine and puts it at the base of aluminum, and then it takes the 3 on aluminum and puts it at the base of chlorine. And then at this point, we can just go through and remove any 1s, and then what we end up with is AlCl3. So it's however you are most comfortable coming up with this formula. Are you going to use the crisscross method, or are you just going to look at it in terms of how many of one do I need to be equal but opposite the other? Either way is appropriate, whatever gets you to the right answer. Another one is magnesium iodide. We follow the same format. We take their symbols first. Magnesium is Mg. Iodide, in its elemental form that we would find on the periodic table, iodine is I. And this should be a capital I. Fonts can look a little bit different for capital I's. But what we want to do now, we have to remember that they're neutral. Charges have to balance, and that tells us how many of each we need in order to balance the formula. We know that the charge on magnesium is positive 2 because we labeled it on the table. And again, if you did not label those, go back and do that. Iodine, negative 1. So we use the crisscross method here. Or how many of one do we need to equal how many of the other? We can see magnesium has a positive 2 charge. So we are going to need 2 iodine to balance out the charge of 1 magnesium. Or crisscross method. Take the 2 from magnesium and put it at the base of the iodine. Take the 1 from iodine and put it at the base of magnesium. Remember, if we do it that way, we end up with Mg1, I2. So we just have to remember that I's are implied as long as the element symbol is there in the first place. So the Mg1, I2 is not necessary. We can just simplify that to Mgi2. Take a minute. Practice these problems, see if you can come up with the correct answer. If I've given you the formula, I would like you to try the name to come up with the name. And if I've given you the name, I want you to come up with the formula. The last 2 were there to trick you a little bit, so do the best you can with those. For the first one, we have Rb2O. So all we need to do is find the dividing line between the cation, or the positively charged ion, which is the metal, and the negatively charged ion, or the anion, which is the non-metal. So all we're doing here is naming the cation, naming the anion. So Rb, if you look on your table, you'll see that is rubidium. O is oxygen, so we would call that oxide. For aluminum oxide, we're going the opposite way here. We're starting with name and turning this into a formula. So aluminum we know is Al, oxide is O, and now we need charges because we have to remember that ionic compounds are electrically neutral. They have no net charge. We know according to our table, because we labeled the column, aluminum has a charge of positive 3, and we know oxygen has a charge of negative 2. Now this one is a little bit harder to see how many of one we need to balance the other because it doesn't go into it evenly. So instead, Finding the least common multiple is one approach, or in this case, the crisscross method actually works better here. Because if we do this, we take the 3 and put it at the base of the oxygen, and we take the 2 and put it at the base of the aluminum, we end up with Al2O3. And that's our formula. For the next one, potassium sulfide. So we know potassium is K, and according to our labeled columns on the periodic table, has a charge of positive 1. We know sulfide comes from sulfur, which is S, and according to our labeled columns, has a charge of negative 2. So we can see here, either through the crisscross method or balancing charges, that we would need 2 potassium to balance the charge of every 1 sulfur, because now if I have 2 potassium, that gives me a net charge of positive 2, and that exactly balances the charge on sulfur, which is negative 2. Now for the next two, we can see that in both cases, the cation, or the first element, is Fe, and Fe is iron in both cases. And we can also see that Cl is chlorine. Now remember, if we are changing these names to turn it into compound form, we need to show that it is bound to iron, and we do that by changing the name, the last part of the name from INE to IDE. But we have a problem here because we can see that both of these compounds would now be named iron chloride. So this is why it's important to have a system for naming compounds, because we run into issues like this where we could potentially be giving them the same name. But as you can see, the formulas for these compounds are very different. So we have to take that into account when we're coming up with the name. And that's what the next section is about. The next type of compound we have is a type 2 ionic compound. So the type 1, or the easiest type, that's just a nonmetal and a metal with a specified charge. So they're the ones we talked about that we circled in red in the beginning, the first two columns, and zinc and silver, because they only have one type of charge. Type 2 are a little bit different. Again, they're a metal and a nonmetal, something from the left side of the table and something from the right side of the table. The cation is still named first, and it still takes the element name. This time, it can have more than one possible charge. So this time, our cation will come from that transition metal area in the middle. Remember, we said those were a little weird, and they can have more than one charge because they behave a little bit differently. So this time, our cation is going to come from that 10x4 block in the middle of the periodic table, or tin or lead, as we circled and shaded in as exceptions to the plus or minus 4 column. So everything in the middle plus tin or lead. And we indicate the charge using Roman numerals. So remember Roman numerals, we're looking at 1, 2, or I. Number 4 is IV, 5 is V, and you can put the lines on the top and the bottom, or you can just leave them off. Either is fine. VI, VII, VIII, IX, and X. So remember, those are our Roman numerals. The second part is the same. We are still going to name it like we would any normal anion or negatively charged ion. We are going to take the anion and use that name second. And again, we use the root of the anion plus the IDE ending to show that it is in a compound at that point. So looking at this one, notice how lead has a positive 3 charge, and we'll go through how to determine the charge in a minute. But when we name it, we name the Roman numeral. We use the Roman numeral to indicate the charge on the cation. So when we undo our crisscross, we see that lead has a positive 3 charge, and that's where the 3 goes. It goes after the cation name, in the middle of the compound. Notice the end is the same. It's still chloride. Nothing has changed about the name of the anion because still anions can only have one type of charge. The only thing that's changed is specifying the charge on the cation using a Roman numeral. FeCl2, notice we have a charge of positive 2 on iron, and we'll go over how to determine that in a minute. But because we have a charge of 2 on the iron, and iron falls in that area in the middle where we do have to specify a charge, we put the Roman numeral after the cation because that's what can change. The anion stays the same, so we leave that part alone. The Roman numeral goes right in the middle of the compound. And this time, since we determined the charge was positive 2, the Roman numeral is 2. And for the last one, CuCl. So in this case, Cu or copper has a charge of positive 1. And again, the Roman numeral goes right in the middle of the compound because it is specifying the charge on the cation. The anion is the same, it's left alone. Now, how do we determine the charge on one of these compounds? So say I give you FeCl3 as your formula, and you need to figure out the name. So there's a couple of different ways to look at this, and the first is the reverse crisscross. So taking the formula, you're going to take the subscripts that are either there or implied to be there in the case of something like a 1, and then you're going to reverse them back to their charge positions. Notice, and this is where a lot of people make mistakes, the positive and negative signs are accompanying the charges, but once those numbers become subscripts, they are no longer positive or negative. So we're basically undoing what was done to this compound in order to determine the formula. The 3 comes back up to the top of the iron, and the 1 comes back up to the top of the chlorine. Now, when we do that, we can see that that puts a charge of positive 3 on the iron, which is where iron 3 comes from. And chloride stays the same because chloride is always going to have a charge of negative 1. Now, if you do this incorrectly and for some reason you get chlorine with a charge of negative 3, you know that can't be right because on your periodic table, you labeled the chlorine column or everything in that halogen column with a charge of negative 1. So go back and check the charge of your anion, and if it matches what you have on the periodic table, then you did fine. Now, the other way of looking at this is to start from a place of knowing the charge on the anion. So you know the charge on the anion is negative 1. And in this case, there are 3 of them. So the total charge contribution from chlorine in this case is negative 3. What does the iron have to be to balance that out? It has to be positive 3. So you know the charge on iron in this case has to be positive 3. Whichever way works for you is fine. Assigning the charge on the anion, multiplying by how many are there to determine the total charge contribution from the anion, and then balancing that out with the cation, or doing the reverse crisscross. The reverse crisscross has some limitations, which we'll talk about in a little bit. Going the other direction, so if I give you the name and ask you to come up with the formula, we have iron 3 chloride. We know iron is Fe, chlorine is Cl, and we also know their respective charges. We have to remember this is still an ionic compound. We still have a cation, which is a metal, and we still have an anion, which is a nonmetal. So we need to know that their charges have to balance. I have to have a neutral compound as a result. So in that case, I know that the charge on iron is 3 because I can see right here I have 3. And I know that chlorine has a charge of negative 1 because that's how we labeled the table. Anions have set charges. So at this point, we're back to where we were with type 1 ionic compounds, and all we're doing is crisscrossing the charges in order to make the formula. We bring the 3 down to the bottom, and we bring the 1 down to the bottom. And then remember, we leave the 1 off because it is implied as long as the element symbol is there in the first place. Take a minute to practice turning these type 2 cation names into formulas, and then the formulas into names. For the first one, nickel 2 chloride. We can look at the periodic table and see that the 2-letter symbol for nickel is Ni. We should know chlorine by now. We know that that's Cl. We know, according to the table, that chlorine has a charge of negative 1. And we know from the name that nickel has a charge of positive 2. So that's where the charge comes from. It's the Roman numeral inside parentheses. So we know this is a positive 2. So for this one, we could crisscross the charges, Or we could figure out how many of one we need to balance out the other one. We can see that nickel has a higher charge, so we're going to need more chlorine to balance that out. Or using the crisscross method, we can see that we have Ni with a 1 that I'm going to leave off because the element symbol implies 1 already, and then Cl2. Applying the same logic to the next one, lead from the table is Pb. We can see that it has a charge of 4 as indicated by the Roman numeral in parentheses. That's 4 positive. And then fluoride comes from fluorine, which has a charge of -1. Same logic, crisscrossing the charges or seeing how to make them equal but opposite. And we can see that if we do that, we will end up with PbF4. For the next one, this is when the crisscross can be just a little bit tricky because if we start with something like PbO, we're assuming that these are ones. And if we're assuming that they're ones, then what we get is something like this. But the problem with this is that we know oxygen does not have a charge of -1. We know that oxygen has a charge of -2. So what we would have to do is to come through here and multiply the charges to reflect that. We would have to multiply the charges by 2 to reflect a charge of -2 for oxygen. But we have to remember we can't just multiply oxygen by 2, we have to multiply lead by 2 as well. So what we would get is lead with a +2 charge and oxygen with a -2 charge. And we can see that this would then be lead with a 2 in Roman numerals in parentheses, and then oxide at the end. Now, the better way to approach this would be looking at the formula, something like PbO again. We know the charge on oxygen is -2. And since there's only one of them, the total charge contribution from oxygen is -2. Lead would then have to have a charge of +2 to be able to balance that out. So that's my preferred method because it gets me to the appropriate answer a little bit quicker without having to adjust the charge as much. Now, MnO2 puts us in a similar position, so we have two options here. Let's look at reverse crisscross first. So if we do reverse crisscross, we get Mn with a +2 charge and oxygen with a -1. Again, the problem with this is that we know oxygen has a -2 charge, so we would have to come through and multiply the charges by 2 in order to make the correction. So manganese would then have a charge of +4, oxygen would have a charge of -2, and then we could name this appropriately as manganese 4 oxide. The other way to approach transforming the formula would be to start out by labeling the anion with its appropriate charge, and we know oxygen has a charge of -2. If I multiply that by the 2 in the formula, that gives me -4 overall, which gives me a charge of +4 for manganese. Again, you get at the same answer either way. It's just whichever method you choose to use. So again, we've got our two methods here. Both of them get you to the correct name. So whichever one you choose to use is fine. For section 5.3, our aim is to learn how to name a compound containing only nonmetals. Now, this is a covalent compound. It's slightly different than ionic compounds because remember what had to happen with ionic compounds is they had to transfer those electrons. And it's the transferring of electrons that turned them into ions in the first place, which is why we call it an ionic compound. But if we are looking at a covalent compound, this is a sharing of electrons. So we are not using the charges as indicated by the table in this type of compound, but we do need to know how to recognize it. So what we need to know here is that since it's a sharing, we're not looking at ionic transfer, we're looking at two nonmetals or two things from the right side of the table here. It's named in a similar way as ionic compounds. The first element is named first. The second element is named as though we would name an anion in an ionic compound. So in other words, we change the ending to IDE. Even though we're not technically talking about an ion here, we're still talking about the second element that's going to indicate that we don't just have two individual elements, we've got two elements bound in a compound. In this case, we're going to use numeric prefixes to indicate the number of each element. Again, this type has nothing to do with charges. So we're not looking at charges, we're not looking at crisscrossing here. We are only using prefixes to indicate the number of each element or the subscript on the element. And then we never use mono for the first element. So you've probably seen this one, CO2, you know that's carbon dioxide. There's only one carbon, but we do not say monocarbon dioxide. We just say carbon dioxide. So I would suggest using something like this as an example on a note sheet that you may make for the test. Write out CO2, write out carbon dioxide, and this just by itself tells you all the rules for naming compounds like this. So what we have to know first is the types of numeric prefixes that we're going to be using, or what those prefixes are. So you should have a space in your notes to write this down. We know that the prefix for 1 is mono, 2 is di, 3 is tri, 4 tetra, 5 is penta, 6 is hexa, 7 is hepta, 8 is octa, 9 is nona or nona, and 10 is deca. So we have just a few examples here. CCl4, carbon tetrachloride. Notice it's not monocarbon tetrachloride, and notice we are not doing anything with charges here. The tetra refers to the number written as a subscript. The only difference here is the subscript comes after the element, the prefix comes before the element name. So we're still dividing this in the same place as we move from formula to name. We just don't have any plus or minuses, any crisscross. The prefix that comes before designates the subscript on the element. So in this case, nitrogen monoxide, we separate one element from another, and as we move from formula to name, one nitrogen, so we just say nitrogen, one oxygen. In this case, we would say monoxide because mono is okay to use for the second element, but not for the first. Notice we do not write monoxide. We need to take out one of those O's, and it doesn't matter which one because there's just going to be one there anyway. So monoxide. NO2, again, separated in the middle. That can help you determine first element from second element. Nitrogen, there's only one because there's an implied subscript of one. So we have nitrogen, and then we have oxygen, or what would be oxide. But since there are two of them, we have to show that with the prefix. So NO2 becomes nitrogen dioxide. So notice why this naming system is necessary, because we can have a compound that is NO, or we can have a compound that is NO2. Both are nitrogen and oxygen, but we have to have some way to differentiate one oxygen from two. And that's just putting the prefix in front of oxygen to tell us how many are there. Take a minute, pause your video, practice the following problems, and then we'll come back together to look at the answers. So as we just saw, NO2, we can start by naming our elements. So we have nitrogen, and then we can start by writing the name of the second element, which is oxide. Remember, we're naming it as an anion, so it's going to have the IDE ending. And then we just want to look at the number. If there are two, the prefix on oxygen, because remember that 2 only applies to oxygen, becomes di. So it becomes nitrogen dioxide. For the second one, we have carbon, and we have oxygen, which again becomes oxide. We have one carbon, but we don't use mono on the first element, so that remains carbon. We have one oxygen, so that becomes monoxide. For the next one, we have carbon again, And again, we have oxide, but this time we have 5 oxygen. So we have to show 5 oxygen, and we do that by writing pentaoxide. Now, you might see the term pentoxide, which still means the same thing. It's common practice, even when the vowels are not the same, when you're putting a prefix and a word together, to get rid of one of those vowels. However, we cannot get rid of the O, because what we're dealing with is not a compound called pentaxide. We have to keep the name of the element intact. So we actually have pentoxide. I've seen it both ways, pentaoxide and pentoxide. They both mean the same thing. H2O. You might recognize this as just regular old water. However, it does have a systematic name. And if we start by naming it just by the elements that we see that we have hydrogen and oxide, but we have some prefixes here that we need to include. Notice we have 2 hydrogen. So if we have 2 hydrogen, we need to say through a prefix that we have 2 hydrogen, which would be dihydrogen. 1 oxygen, and we are allowed to put a prefix on the second element when there's only 1. So we would say dihydrogen monoxide. For BF3, we have boron, and we have fluorine, which becomes fluoride. We have 1 boron. Again, we don't need the prefix mono in front of boron. We have 3 fluorine atoms. So this becomes trifluoride. Boron trifluoride. Sulfur pentafluoride. Sulfur we know is S. Fluoride we know comes from fluorine. And we know that penta means 5. So this now becomes SF5. Now, one of the reasons that it's important that we are scientifically literate is because we want to be able to pull out fact from fiction as it makes its rounds on social media. So one of the things that makes its rounds from time to time is this DHMO conspiracy. So DHMO is often just stated as DHMO, or in other words, dihydrogen monoxide, without giving too much background on the material that we're talking about. And if you use, I don't know, what are they now, Twitter or Instagram, these things make the rounds, and they're to comment on how the government is not regulating things like DHMO. And if you're aware of this type of thing, if you're scientifically literate, if you understand what these words mean, then you won't be trapped by these types of propaganda. So, yes, inhaling it can kill you. It improves athletic performance, found in every lake, river, and ocean, major part of acid rain. It corrodes metal. Um, uh, a lot of these different type of scare tactics are used to say that it does things like cause severe burns. Yes, it does. It's been found in excised tumors of terminal cancer patients. Yes, of course it has. Industrial solvent and coolant found in nuclear power plants used in the production of styrofoam is a fire retardant. In many forms of cruel animal research, yes, that's all true. But remember, what you're dealing with is water. So it's very important that you don't fall into traps like this and fall for these scare tactics. And being scientifically literate can help solve that problem.